Welcome back. We're on lecture 12. We're going to be talking about absorbing chains. And this is our penultimate lecture in the series of Markov chains and affinity. Um, and here, in this lecture, we're going to cover another class of Markov chains that behave well in the time goes to infinity limit. In the previous lecture, we talked about the Perron-Frobenius theorem, which guarantees the limit. And in that case, we had the conditions aperiodic and irreducible that guarantee that there's a limiting distribution and that the probability of each state is not zero, it's greater than zero. In this case, we still have limits that exist, but now we're in a different scenario where the probabilities are not going to be all greater than zero. There's going to be some states which are going to attract all of the probability, and these are going to be absorbing states. And this is going to break the condition of the Perron-Frobenius theorem where you have your chain to be irreducible. In particular, you're going to have more than one communication class appear. And so in the lecture, we'll start. I want to motivate all these topics through specific examples, the simplest examples of non-trivial absorbing chains, and try to motivate certain questions about these absorbing chains. And some of these questions are going to be, how long does it take to go to the absorbing states? And what's the probability of going to one absorbed state versus the other? And stuff like this. And in the process of answering these questions and motivating these questions, I'll also add some technical details such as the strong Markov property. So let us get started. That's better. Wow. Technical difficulties. Let's see if we can figure it out. There we go. Technical difficulties resolved. Okay, so again, this whole discussion I want to motivate it through specific examples. And one of the specific examples is this Markov chain. And right off the bat, we can tell that this is not irreducible. It is aperiodic, meaning that all states have period 1. And the question is, what happens when t goes to infinity? And here, as I mentioned, it's not going to be irreducible, so we're going to have two communication classes, which implies that it's not irreducible, and it's going to be aperiodic. And in here, really, since period is a class property, we should do it for at least one element in each communication class. So since there's self-loops in each of these communication classes, in this communication class and in this communication class, that means that the period of this communication class, d is equal to 1, and the period in this communication class is equal to 1. So it's got to be aperiodic. But we're interested, so in here, this is just to set up the fact that the Perron-Frobenius theorem doesn't apply, and taking the limit as t goes to infinity, we can't use the Perron-Frobenius theorem. But we want to consider what happens as t goes to infinity. So in here, we are going to, first we represent the transition matrix this way, and this is going to be, and then the claim really is that the limiting distribution, or the limit of the transition probability as t goes to infinity, is going to be equal to this 0, 0, 1, 0, 0, 1, 0, 0, 1. And here I'm not giving you the computation, and in fact I didn't do the computation, I just obtained this result intuitively and heuristically. And how do I arrive at this? And here the thing that happens is that if you start at 3, you're just going to stay in 3. And in fact, anytime that you arrive at 3, you're going to stay in 3. So whatever probability mass or probability density we have in any of these states, eventually is going to make its way to 3. So if we start with any mass in here in state 1, we can go here, and if we go to 3, we're going to be doomed and we're going to stay in 3. But there's different ways that we can get there. We can go here, then we can go back, then we can go back, then we can go back. But eventually, we're going to be leaking some probability density out to state 3. And once we get into state 3, then we can't get out. So you can think of it almost as a black hole, if you will, where you can't escape it anymore. And then by getting to state 2, you get close enough and you are slowly but surely losing probability density to state 3. And as time goes to infinity, you're just going to lose all your probability density. So in here, we have that this is going to be equal to 0, 0, 1, 0, 0, 1, 0, 0, 1. And we'll see later on in a computation how you can start to figure this out. But still needs a little bit more technicalities, but it's going to turn out that this is the case for this transition probability. And this corresponds to a collection of Markov chains that are called absorbing Markov chains. And in here, 3 is an absorbing state. And absorbing Markov chains are characterized by having a transition probability of this form. And here, where you have Q, where you can break it into block form, where you have a corner where it's the identity, and then the segment on the left is going to be equal to 0. And here it really means, so this structure really is representing the fact that in here, 3 is not going to communicate back to 1 or 2. So there's no way to escape 3. And in addition, it's gonna say that once you're in 3, you're gonna stay in 3. And if we were to have a larger Markov chain we could have multiple absorbing states, such as 4, where 4 jumps back to itself, and then you would have that 4 goes to 4. So you have to have that this lower right corner is exactly the identity, meaning that once you arrive to one of the states in here, then you're just going to stay in that state and you're not going to move to any other state, not even any other absorbing state. So the key for this absorbing chains is that you have absorbing states, which are states that only have self loops with weight 1. And potentially by relabeling the states, you can always get the transition matrix into this format where the lower right corner is just an identity matrix whose dimension is equal to the number of absorbing states. And then here, this Q matrix really represents the interactions between the non-absorbing states, which are these, and then the R vector or R matrix is going to be the interactions between the non-absorbing states and the absorbing states. So in here you see that this is the interaction which corresponds to this. So these are going to be the type of Markov chains that we're going to consider in this lecture. And in here, the first question of what's the limiting distribution, it's fairly straightforward. And in particular in here, we'll see in this, especially when there's only one absorbing state, we see that the limit is just going to be 1, 1, 1. So it's not particularly interesting at this point with that one absorbing state, and we'll consider it in more detail with more absorbing states later. So here, let me introduce a few terms of recurrent and transient states. And for this, I need to introduce a random variable t sub j. T sub j is going to be the first passage time to state j. So it's the first time the Markov chain reaches state j for time n greater than 0. And what we're going to do is we're going to define a recurrent state j if the probability that you reach state j in time less than infinity is equal to 1. So you're going to keep coming back to the state with probability 1. And the opposite term would be a transient state, where the probability of returning or arriving at state j is in finite time is less than 1. So that means that you may, if you start your Markov chain, you may never reach state j, starting from state j. So these are going to be these two different types of states, recurrent and transient. And if we look at our example that we have right here, these are going to be transient states, and this is going to be a recurrent state. And essentially, the reason why these are transients is that if you start in 1, there's a non-zero probability you may never return, because you could go here and then you can go here and then you never return. So these states are going to be transient. And the same thing happens with 2. And 3 is going to be recurrent, because if you start from 3, you're always going to return to 3. And we actually want to characterize more precisely how to determine whether a state is transient or recurrent. So for this, to obtain an alternate characterization, we're going to introduce the strong Markov property. So the strong Markov property is, I need to introduce a bit more notation, but in particular, it means that first we need to introduce a stopping time, which is a certain rule that for your Markov chain that determines whether you've achieved a certain goal based on your Markov process. So if you think of the gambler's ruin example, for instance, where it's a betting game where you're moving up or down by 1, depending on your bets and the outcome of the game, then you can think of it as so that you have this Markov chain, and then a stopping time would be a rule that tells you when to stop playing. And in the gambler's ruin example, the rule is either you reach 0 or you reach a certain amount of money, and that's going to be a stopping time. And in particular, in technical terms, the condition that you need for a stopping time is that the events determined by t, the stopping time equals t, are going to be in the sigma algebra generated by x0, x1, all the way to xt, which really says that the rule to stop at time t only depends on the outcome of this Markov of the Markov process up to time t. So for the strong Markov property, we have the following claim, and this that if xt is a time homogeneous Markov chain with transition matrix B and t is a stopping time, then the transition probability from xt, the stopping time, is equal to I, to the Markov chain at the stopping time plus n is equal to j, is just going to be given by the nth step transition probability of the Markov chain. So we're going to forget about the stopping time, essentially. And in particular, this means that the Markov chain YT, which is X sub T, this stopping time plus T, is a Markov process. So, and we've seen this before, that due to the timing homogeneity, we always had this property. If for instance capital T was a deterministic time, if it was just a fixed number k, then we've seen it before that this is going to be a transition matrix, that the transition probability is going to be given by this transition matrix, and that this would be a Markov process also. And here the extra layer is that capital T is a random variable, so somehow that could introduce randomness to remove the Markov property. But this randomness that's introduced actually doesn't actually keeps the process a Markov process, which is not necessarily clear. So let me go through the proof of just this fact. This is the necessary fact that we'll need. And we just want to compute this transition probability. Let's see. We were coloring T green. T, 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 T. So let's compute this transition probability. So first I applied the law of total probability, and I used a weighted average with the conditional probability, and I considered the possible cases of the stopping time, T is equal to S, and I average through all the possible outcomes. And in here, I use the typical Markov property. So we have, by the definition of stopping times, T only depends on x0, or T is equal to S, only depends on x0, x1, all the way to xs. So this conditional probability is going to depend on xs and all these other states, but due to the Markov property, we know that this transition probability only depends on the most recent information, xs, which we already know by this condition. So this stopping time, T equals to S, is not adding any new information that we need, since it's only depending on the past and xs, and we already have this information here. So this conditional probability is in fact independent of this stopping time. So we can just forget about this, and we can use the Markov property to do that. So now we arrive here. And now we just use the timing homogeneity property of this transition matrix. And this is actually a typo. This is T, 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 T. So this transition probability is going to be given by the T-step transition matrix. And this is independent of S, so we can factor it out. And then we just have the summation. And this probability is going to be finite. So this is the sum over all the possible cases for T, and it's going to add up to 1, because the total probability is equal to 1. So we see that in this case, this is going to be equal to 1, and we obtain this transition probability. So this is the Markov property. And this is the property that I want to use to prove this following claim. In here, this is going to be an alternate characterization, the original characteristic of transient recurrent states. The original the original definition of a recurrent state is that with probability 1, you're going to return to the same state in finite time. So this is just a probability that you're going to return. But intuitively, if you return with probability 1 to the same state, then you should keep returning to that state next time. So if you go there, if you start there in a state J, then you're going to return with probability 1. And then after you return, then since it's a Markov process, then you should also return with back with probability 1. And each time that you arrive back, then the next time there's going to be a probability 1 to return. The subtle thing here that, and so the interpretation of this, or the way that you can think about it, is that if you run your chain for an infinite amount of time, then this should imply that the number of times that you visit the state J is going to be infinity, because each time you return, there's going to be probability 1 of returning. So at infinite time, you're just going to be there an infinite amount of times. And so this is going to be the first claim in this. So here I'm motivating this direction of this first claim. And it turns out that it's an if and only if statement. That a state is going to be recurrent if you visit that state an infinite number of times in expected value, that is. And it turns out that the opposite is true, that if a state is transient, meaning that heuristically a state is transient if there's a non-zero probability of never returning to that state. So using the same type of intuition, if there's a non-zero probability of never returning, then once you leave that state, then you might never return. So in that case, turns out that if you run your chain for an infinite amount of time, the number of times you visit the state is going to be finite, because there's a probability of not returning. And this is this claim. And here I introduce some technical, this is actually this, some technical notation to actually precisely capture these ideas. So I'm going to introduce this random variable Jn, which I call an occupation variable of state J, which is really just an indicator function. Jn is either going to be 1 or 0, and it's going to be 1 if at time n you're in state J, and it's going to be 0 if at time n you're not in J. So you can see that if we sum from n equals 1 to t of this occupation variable, then this is just going to count the number of visits to state J by time t. Whoa. And the claim then is recurrent if and only if the expected value of number of visits to state J by time infinity is equal to infinity. And transient if the expected number of visits of state J by time infinity is finite. And the subtle thing here in this argument, this heuristic argument that we made, is that once you, for instance, in the recurrent case, once you return, then since it's a Markov chain, you expect the first return time, you come back with probability 1. So you're guaranteed to come back to the same state. And then what we expect is that since the probability to return was 1 initially, then the probability to return after that is going to be also 1. But the subtle thing here is that the probability to return is a random variable. The time at which you return is a random variable. And after that time, you essentially want to start the Markov chain again from the beginning to actually start the random process. But this is where we need the strong Markov property, because this is going to be a random time where we start our Markov chain again from scratch. We want to think of starting the whole process from scratch. But it's going to start only after a random time, which is the time when you come back. And so we'll need the strong Markov chain to prove this statement. So that's what we introduced in the previous slides. So let me go through the proof of this. So, and then here I'm sneaking in this equalities of this expected value. But and that's what I'm going to prove first. In both cases, we have this equality of the of the expected value. And in here, this is showing this equality is not too difficult. We start with the left-hand side, and we use linearity to take the expected value inside the sum. And then this is an expected value of an indicator function, which is just the probability of the event, of the conditional event in this case. And then this we can just write it using the transition matrix. And we obtain this summation. And people write it this way because sometimes it's easy to approximate this quantity, and you can approximate it, and you don't have to use very sophisticated approximations to either show that it's finite or infinite, and then you can then claim that it's recurrent or transient, the state. So this is just a quick computation showing this equality. Now, what we actually want to show is what we want to compute actually is the probability to return m times in time less than infinity. So what we've actually thought about already, or what we've used to classify states either as recurrent or transient, is the probability of returning one time. So if you start in J and the probability that you return again is less than the probability that you return in finite time is equal to 1, then it's going to be recurrent. If this is 1, then this is recurrent. If this is 0, this is going to be transient. Recurrent, transient. So this probability is what we've used to classify recurrent and transient, where T1 is the first time you return. But then to actually prove the claim, I actually need to consider the mth return time. So the probability of starting in position J and returning m times to the same state in finite time. This is what I need to compute. And in here, this is where we'll use the strong Markov property and how we'll prove the result, computing this probability. So again, I'm going to use the law of total probability. I'm going to break it up into, I'm going to condition on the previous return time on Tm minus 1. And I'm going to condition it in two cases, whether it's finite or infinite. But in fact, in the case that the return time is infinite, of m minus 1 returns is infinite, then this is going to force this Tm to be infinite. So that case is not going to contribute to a probability. So by doing the law of total probability, we actually have only one case to consider. And again, this is because Tm minus 1 is equal to infinity clearly implies that Tm is equal to infinity. So this cannot be true for the other case, Tm minus 1 equals infinity. So in the law of total probability, only this term survives. And in here, I want to translate what this probability of what this event means and into the Markov chain. And what it really means is that at time Tm minus 1, we're in state J, and then at some later time, Tm minus 1 plus L, where L is 1 through infinity, we return to J. So this probability, I'm going to write it this way, so that we arrive at Tm at some random time, we arrive at J, and then after that, we're gonna come back to state J. So I'm rewriting this. And now, this is where I can use my strong Markov property. I can just shift to the original. I can just forget about this T using the strong Markov property. And I can just have the time that I arrived at J, that I can just think of it as starting the Markov chain from scratch, from time 0. and then this is just going to be the 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 collection of events where you start at state J, and then at a later time L, you are in state J again. So this is gonna be this is gonna be this is gonna correspond, this event is gonna correspond to the first return time, to T1. And because effectively what we've done with the strong Markov property is that from this random time, we started the chain again from zero, from scratch. And then starting from scratch, then the probability of this event is just going to be the probability of returning to state J. And this probability is going to be equal to P, given above here. And then we have that this probability of Tm less than infinity is going to be equal to P times the probability of Tm minus 1 less than infinity. And then by induction, we can deduce that this probability is going to be P to the M. And here we really use this strong Markov property to compute this probability. Now let's use what we've learned to compute it. And here I'm actually going to use a different way to compute the expected value rather than the computation I gave at the beginning with the transition probabilities. And here, first of all, I'm going to use this formula for the expected value. And here I'm going to recall it that for a discrete positive random variable x, then I'm going to use z because x is this is going to be equal to probability that z is greater than or equal to m for m is equal to 1 to infinity. So this is an alternate formula for when c is greater than or equal to 0 and discrete. And this is the formula I'm using to go from here to here. Now, I note that this event in the probability corresponds to the event of visiting state J at least m times or more. And this event of visiting the state J at least m times actually corresponds to the fact that the time of the mth visit is going to be finite, which is what we computed in the previous slide, and it's equal to PM. And we obtained that this probability is just going to be this geometric sum. And now, depending on the value of P, if P is less than 1, then we have a finite sum. And if P is equal to 1, then we have an infinite sum. Then we obtain the expected value, either transient or recurrent. So in here we see that this expected value is going to either be finite if the chain is transient or infinite if it's recurrent. And this is going to be an if and only if computation. All right, so let's go back to the statement. Recurrent if the expected number of visits is infinite. Transient if the expected number of visits is finite. And to do this, we need the strong Markov property, which tells us that after after a random stopping time, we may start the Markov chain again from scratch after that time and have the same properties. All right, so I really want to use this result to motivate the next following questions. The first question is for transient states, based on the previous result, we know that the expected number of visits is going to be finite. And it turns out that for absorbing chains, then we can actually compute this expected number of visits before we go to an absorbing state. And it should be a finite number. For the absorbing states, the expected number of visits is going to be infinite. So the interesting question is determining the expected number of visits to this state before going to an absorbing state. So the question here is going to be the expected number of visits before reaching state 3. And here we're going to one second. And here we're actually trying to determine more roughly what is the expected amount of time that we spend in this transient states before arriving to state 3, since we're only expected to be here a finite amount of time. So this is what this random variable is the expected, the amount of time in transient states. And what we want to compute is these two cases, the amount of time spent in transient states. If you start from 1, the amount of time in the transient states if you start at 2. So the way that I'm going to answer this question is using a common technique of running the Markov chain for one step and setting up a system of equations, and then solve for the random variable. So the first thing is to use the law of total expectation to write this and condition on the chain at time 1, and writing it explicitly, this expected value, then I consider the different cases for x1, and I weigh according to the probability of those cases. These probabilities are going to be given by this transition probabilities. And again, since it's a Markov chain, this conditional probability is only going to depend on the latest, most recent information. And we can shift everything. So in here, this expected value is going to be equal to the time plus 1. So we've already taken one step to 1, and we're starting from 1, and so it's going to be the same expected value as starting from t as starting from 1, and we've already taken one step, and it's going to be the same amount of time as if it started from 1. And similarly for 2, we've taken one step, so the time is going to increase by 1, but it's going to be the same. The expected value is going to be the same as starting from t, as the expected value of t starting from 2. So this, I write it as this, because I ran the Markov chain by one step, so that's 1, and now it's as if we're starting from time 2. And then if I ran in one step, I have x1 is equal to 3, and at this point, I already know that the amount of time it took me to reach state 3, which is this random variable, is going to be equal to 1. So the expected value here is just equal to 1. And by factoring this 1 from all these expected values, I just have P1 to 1, 1 times P1 to 2, and 1 times P1 to 3. So this is just the sum. If I just consider all these ones, 1 and 1, then it's going to be the sum of this transition probabilities, which adds up to 1, because 1 has to go either to 1, 2, or 3. So this is going to be a 1. And then I have this equation for if I start in 1, it's going to be equal to this. And then I can set up a similar system of equations if I start from state 2. And again, I have the same type of feature where it's going to be 1 plus this weighted sum of conditional expected values. Right here, I have the transition probability starting from 2. For this one, I have the transition probability starting from 1 and then going to 1 or 2, the rest of the transition states. So I have a system of equations for this conditional expected value. It's going to be 2 unknowns and 2 equations, so I can just solve for it. And in particular, I have that I set up this vector v, which is contains the conditional expected values that I want to compute. And the system of equations given here are actually corresponding to this matrix equation or this vector equation. V is equal to the vector 1. Here, vector 1 is 1, 1, plus Q, coming from this Q here. So this times V, which are these. So this is my system of equations with 2 equations, 2 unknowns. So I can just use linear algebra to solve for it. And then I have that V is going to be equal to this. So in this specific example, and this is a general recipe that applies to any absorbing chain. And we'll see that in a second. But for this particular example, we have Q is equal to this matrix. So ID minus Q is going to be this 2 by 2 matrix. And then if you take the inverse, we obtain this. And then this, based on the previous slide, is equal to B. It's going to be equal to ID minus Q inverse. So it's going to be this times 1, 1. And I get 4, 3. And by the way that we define V, that means that the expected number of time in the transient states, given that we start at x at 1, is going to be 4 steps. And the expected number of time in the transient states is going to be 3 if we start from state 2. And this is similar to the mouse and maze problem in chapter 1. But this is more general. And you can think of the absorbing state as the cheese and the maze as a transient state. And now, in the general case, let me set up the formula. And it's going to be the same type of computations. We're going to have transient states labeled 1 through m, and absorbing states labeled m plus 1 through n. And we're going to have a decomposition of the Markov matrix into block form, where this are all the transient states, and this is an identity matrix corresponding to the absorbing states. Again, the absorbing states all have self-edges with weight 1. So we have an identity matrix. And so this is the interaction among the transient states. This is the interaction among the absorbing states. They only communicate with themselves. And this is the interaction between the transient states and the absorbing states. And in here, this Tj is going to be, I need a J, in fact, T. This T is going to be the amount of time you spend in the transient states. So the time it takes you to reach an absorbing state. And we're going to denote this vector V by this expected value. And using the same ideas as in the previous computation, we can actually compute this expected values using this formula. And in here, the example that we just computed, we had Q be a 2 by 2 matrix, but in general it can be a higher dimensional matrix, which in that case you would use a computer to actually compute the inverse of this matrix. But so you might use technology to solve this type of problems, but at the end it's just a linear algebra problem. Now I'm going to conclude this lecture trying to consider a different problem with the absorbing states, and absorbing chains. And here again we're going to have this transient states, and I'm going to consider a slightly more complicated Markov chain where I have two absorbing states. And the question is, you're going to be in this transient state and you're not going to stay there. You're eventually going to go to an absorbing state. The question is whether you go to state 3 or state 4. And it depends whether you're starting 1 or 2. But we want to figure out the probability of going to one of the states. I got the black lung. What is the probability of landing on 4 before landing on 3? So this is the basic question. And here we'll consider two approaches. We'll actually take the limit of PT, or the transition probability as t goes to infinity. And the second approach is going to be similar to the previous approach of running the Markov chain for one step, using the law of total probability, and then setting up a system of equations. And we'll see that we obtain the same answer. So in the first step, we can actually just notice a pattern in the computation for the transition probability. So here we have P is in this form for absorbing chains, and we want to compute P squared, so we do Q R I D 0, and then we obtain this result. By multiplying by that, we have Q squared, QR plus R, and ID. ID stays ID. Then we multiply by the transition matrix again, Q R ID, then we obtain this. And then by continue doing this, you notice that P to a T is actually equal to this. And then taking T to infinity, you have to compute the limits as T goes to infinity of this and this. The claim here, which is not really substantiated and needs a little bit more careful details, is that this is actually go to 0. This actually goes to 0. But we won't prove this, but the basic idea is that since these are transient states, you're losing probability mass to the absorbing states. So the probability of staying here is going to be equal to 0. And here, we use the geometric sum formula, k from 0 to infinity is equal to 1 over 1 minus xk. It also applies for matrices, so we can compute this to be equal to this. And then we obtain that the probability of arriving to the absorbing state J from the transient state I is equal to this. So this is fairly straightforward, but nonetheless, I mean, the technicality is proving that this goes to 0, which it does require some amount of work, but we're just going to skip it for now. Now, the other way to do it is setting up a system of equations by running the Markov chain for one step. And here, the first step is do the total law of total probability by doing a weighted average over all the possible cases of the first step. So all the states K. And here, again, since this is a Markov chain and we can be translation invariant, this probability is going to be equal to this. And this is just going to be the transition probability. And In this summation, we can actually, this is overall state, we can separate it into the states K that are transient and absorbing. We leave all the transient states here, and then if we move to a absorbing state that's not equal to J, this absorbing state, we're never going to reach J. So the only absorbing state that we can reach J from that absorbing state is going to be J. So whenever we break up the states into a transient and absorbing states, in the summation where we have absorbing states, the only non-zero transition probability is the transition from I to J. And this is going to be equal to 1, because the probability of reaching J from J is going to be 1 because it's an absorbing state and will stay there. Now I've set up this system of equations. This probability is equal to this. So I'm going to do the same thing that I did in the previous case for the expected amount of time in the absorbing states. So I'm going to set up this matrix in this case, where it's going to be indexed by the transient states and the absorbing states. And the equation that I've set up is equal to this. And you'll see that this element is Wij. This is only for transient states. So this is Qi to j, and this is W given, no, sorry, this I to k is this transition, and then this is this W. And this is because of the notation that we've discussed before, that from probability to linear algebra, you switch the order of the indices. So this is Ik, so this is Ik. So this is the summation, and then this is the interaction between the transient and absorbing states. So we obtain this system of equations, which we can write them in this following way. W equals QW plus R, matrix notation. And then by regrouping terms, we have this relation, and then we take the inverse of this. And then this is how we find the probability of reaching state J from state I in matrix form. So again, it's linear algebra. And with that, I conclude this section. This is a bit of a handful, so take a close look at it. But I think this is where you start actually seeing the true power of Markov chains and how linear algebra applies to it. In the next lecture, which is going to be the last lecture for this series of Markov chains and infinity, I'm going to work on the proof for the Perron-Frobenius theorem. And it's going to be other miscellaneous proofs that I haven't given for the other sections. But at this point, you should have the formulas and the basic idea of what's going on with this chains. All right, thank you very much. I'll see you next time.